Hello everybody and welcome to this lecture on absorbed dose calculation algorithm, entitled Choosing the Algorithm, Spatial Sampling and Radiation Range. My name is Daniele Pistone and I am a researcher and lecturer at University of Campania Luigi Vanvitelli in Caserta, Italy. I have nothing to disclose in relation to this presentation. Let's start by quickly reminding that internal dosimetry in nuclear medicine aims at assessing the absorbed dose to tissues and organs imparted by the radiation emitted by radionuclides biodistributed within the human body. In order to perform this kind of dosimetry, two ingredients are essential: modeling the human anatomy of interest, which can be specific organs, tissues, or the whole body, and modeling the radionuclide distribution. When the human anatomy is implemented by standardized and healthy whole bodies, historically named computational phantoms, we talk about model-based dosimetry. Such models can reproduce the human morphology with simplified geometrical shapes, like the MIRD5 model, or with voxelized geometries, like the ECRP 110 models, or even with tetrahedral meshes, like the PSRK model. Whatever the type of model, a common characteristic is that each organ has a specific composition and density, and a homogeneous radionuclide activity can be assigned to it. Model-based dosimetry is often used as a reference dosimetry for diagnostics. From the point of view of spatial sampling, model-based dosimetry is an organ-level dosimetry. The larger the range of charged particles emitted from a source organ, or the mean free path if we deal with neutral particles, the higher will be the absorbed dose contribution to the different target organs. A second type of nuclear medicine dosimetry is single organ dosimetry, in which a specific organ of interest is modeled using a spherical model, an ellipsoidal model, or an ad hoc geometry, like the one reported for the choroid plexuses in the bottom right of the slide. This kind of dosimetry is used especially to deal with lesions or with anatomical sites not present in standardized whole body models. In these cases, the focus is put on the specific site, assuming its homogeneous composition and uniform radionuclide uptake. Single organ dosimetry is an organ-level dosimetry and allows to calculate self-absorbed doses, meaning that the source organ coincides with the target organ. In this case, the larger the range or mean free path of the radiation, the less the absorbed fraction will be, as we can appreciate from the example on the right, showing a simulation of the radiation emitted by yttrium-90 above and lutetium-177 below for the same spherical model. The third type of dosimetry is imaging-based dosimetry, in which computed tomography scans are used to model the patient morphology at voxel level, enabling to assign masses and compositions to each of them. PET or SPECT scans are instead used to model the voxel level activity distribution from the radionuclide biodistribution. And the final aim is assessing the absorbed dose in each CT voxel, so that not only average absorbed doses to organs can be evaluated, but also other metrics like dose volume histograms, isodose curves, maximum and minimum values of absorbed doses in organ. It clearly emerges that this is a patient-specific dosimetry, and thus it is mainly used for therapy planning. Being a voxel-level dosimetry, imaging-based dosimetry is at suborgan level, and it allows in principle to account for morphological inhomogeneities and activity non-uniformities. Being based on patient data, it can account both for healthy tissues and lesions. In this scenario, The larger the range or mean free path of the emitted radiation, the higher will be the absorbed dose contribution from a source voxel to surrounding target voxels. Now let's focus on voxel-level patient-specific dosimetry, giving an overview of the four algorithms employed to date: local energy deposition, convolution of dose point kernels, convolution of voxel-less values, and direct Monte Carlo simulation. Local energy deposition assumes that all the energy emitted in a voxel is absorbed in the same voxel, neglecting the cross-irradiation among voxels. Thus, the absorbed dose in each voxel is calculated by multiplying the time-integrated activity for the average energy emitted by the radionuclide of interest and dividing it for the mass of the voxel, deduced from the CT. Local energy deposition is acceptable only for alpha emitters and some beta emitters with ranges shorter than the voxel dimensions. It is clearly not suitable in presence of significant gamma emission and secondary photon emission, with penetration lengths larger than the voxel dimensions. The main pro of local energy deposition is the extreme fastness, since it consists in a simple multiplication. The con is that it is based on a very strong approximation, limited to few radionuclides and scenarios. To introduce the next algorithm, which is dose-point kernel convolution, we have to first introduce what a dose-point kernel is. A dose-point kernel is the radial absorbed dose distribution due to the decay of an isotropic point-like source in an homogeneous infinite medium. Dose-point kernels are calculated with Monte Carlo simulations by scoring the absorbed dose in concentric spherical shells, setting as a radiation source monoenergetic particles or directly radionuclide spectra emitting from the central point. Many dose-point kernel databases are available in literature, like the ones reported in the references. A point-like source is obviously an abstraction, but we can use the superposition of many point-like sources to reproduce the overall activity of a finite region, and as well the absorbed dose in a target point can be viewed as the superposition of absorbed doses due to all these point sources. Mathematically, this superposition can be obtained with the convolution operation, shown graphically on the right, that in dosimetry is exploited to convolute a time-integrated activity map with a dose-point kernel to obtain an absorbed dose map. Dose-point kernel convolution is a quite fast method, usually taking minutes. It is accurate for homogeneous tissues and has the advantage of the availability of many databases and the possibility to be applied also to evaluate absorbed dose rate maps, if applied to activity maps. Its main con is its inaccuracy for inhomogeneous media, like the interfaces between tissues with very different densities. By the way, this kind of inaccuracy can be now reduced with post-convolution correction methods. A conceptually similar approach to dose-point kernel convolution is the one followed by the voxel S-value convolution. Voxel S-values, also referred to as dose voxel kernels, can be viewed as the application of the Mird scheme to voxelized geometries, in which each nth voxel acting as a uniform source for all the surrounding nth voxels. In order to be applied in a dosimetric convolution, the voxel S values are defined in a radial symmetry geometry, generally a cubic one with cubic voxels of homogeneous material, and with the central voxel being the radiation source. So, the voxel S values are basically the voxelized version of dose-point kernels. For nuclear medicine dosimetric purposes, a discrete convolution of a time-integrated activity map acting as the input in the animation on the right, with a voxeless value acting as the kernel, gives as output the desired absorbed dose map. Voxeless values are calculated via numerical integration of dose point kernels or directly via Monte Carlo simulations. The main pro of voxelless values convolution with respect to dose point kernel convolution is its further speed, thanks to the voxel level correspondence between the time-integrated activity map and voxelless values, making the computation less intensive. Unfortunately, this can be also a major con, because it requires the voxelless values to have the same voxel dimensions as the time-integrated activity map of interest, which can have different reconstruction matrices depending on the scanner used. Few databases are available in literature, and for a limited number of voxel dimensions. As always, researchers are finding solutions to overcome these difficulties. Here, some recent advancements and alternatives: introducing density correction methods, resampling the time-integrated activity map or the voxelless value maps to match each other, developing analytical methods for calculating voxelless values. On the right, a list of references for the details. Last but not least, the fourth and final dosimetry method is the direct Monte Carlo simulation. With this term, we refer to a series of statistical and computational methods based on repeated sampling of pseudo-random numbers according to probability distributions set from a model describing a phenomenon. In our field of nuclear medicine, Monte Carlo algorithms can be employed to simulate radionuclide decays and the interaction of their emitted radiation with the human body. Different software tools are available for these purposes, like GEANT4 and GATE, enabling to apply the Monte Carlo algorithm to the physics of our interest, made by cross-sections of interaction in different materials and all of that stuff. By simulating a high number of decay events and tracking the history of the simulated particles, statistical quantities of interest can be scored, like the energy deposited into volumes, and in the case of voxel-level dosimetry, the absorbed dose in each voxel of a patient CT can be evaluated. Here we see an overview of a nuclear medicine Monte Carlo dosimetry workflow. We start from a CT scan to set the voxel-level patient-specific geometry and composition through ounce-field units conversion. A SPECT or PET scan is the input to set the spatial probability distribution of radioactive decays within the body. The emitted particles are generated and their interactions simulated, scoring the energy depositions at voxel level. And after some post-simulation calculations, we have our absorbed dose map or absorbed dose rate map. Direct Monte Carlo simulation is the gold standard for dosimetry, being the most accurate and patient-specific method. It accounts for the cross-irradiation among the voxels, taking into account patient-specific morphological and functional inhomogeneities, and being the most accurate method at tissue interfaces. Consequently, it is usually used as a reference to validate the other approaches and new methodologies. Its main con is the slowness, requiring hours or even days to run, and the expertise required to implement simulations, making it more a research than a clinical method at the moment. Here, a comparison of the four dosimetry methods described as a function of their accuracy and calculation speed. We can see how the two are inversely proportional, and patient specificity goes in the direction of high accuracy but low speed, from LED through convolutions to Monte Carlo. To summarize and conclude this lecture, let's ask ourselves, how do we choose the absorbed dose calculation algorithm? The answer depends on the relation between radiation range or mean free path and the spatial sampling we want to use. Looking at the graph on the right, we first have to ask, is the radiation non-penetrating with respect to our spatial sampling? If the answer is yes, local energy deposition is an acceptable approximation. If not, let's proceed by asking if the medium is approximately homogeneous or not. If the answer is yes, convolution methods are okay. If not, Monte Carlo is still the best solution. All of this within the assumption that the radiation source location is known with good enough accuracy for the chosen spatial sampling, and this depends on the functional tomographic data. But this goes beyond the scope of this presentation. With this, we finish this lecture. Thank you for your attention and enjoy the following courses of this webinar.